action, and then, yeah, it does not seem to work. Oh, does it? Okay, then we'll talk about a few general principles, show you some examples of quantitative theory, and with emphasis on predictive capabilities, and we'll talk about challenges for tomorrow. So many good things happened in nuclear theory, relevant to ISOLDE, both in terms of new ideas and of course, resources, new developments were made possible through vast computing power. And so let us start from something very general. This is the landscape of ISOLDE's physics. This is the nuclear landscape. This is where the action is. Okay? So this, the time scale of the science is basically ranges from QCD transition, which is the development of color singlets. Protons and neutrons formed 10 milliseconds after the Big Bang, and it is continuing till today. So we can roughly say 13.8 billion years. So the distance range, which is of importance for this physics, for the science, is from 10 to the minus 15 meters. This is femtometer, proton radius, to 12 kilometers, neutron star radius. So this gives you the time and distance scale. So the questions which this field is trying to answer actually are also common to other areas of science, but we have some special room in this quest. Okay, so I just listed 4 questions which were put together by US National Academy of Sciences report. So the first question is about the origins. So how did visible matter come into being, and how does it evolve? And this is the question about the origins of nuclei and atoms. How are atoms produced in cosmos? How are nuclei made? The second question is about emergence, about self-organization. How does subatomic matter organize itself, and what phenomena emerge? And the second question has, of course, lots of common points with condensed matter physics and atomic, molecular, and optical physics. The third question is about the fundamental interactions, the physics of the new standard model. And the fourth one was already very nicely discussed today in 2 talks on applications. So important point to be made that science and society they both rely on our understanding of the atomic nucleus and grand nuclear landscape. So we are the group to provide this understanding. Okay, so this is a talk on theory. So let me make some points, general points first. So this nice quote from Pythagoras, who divided the theory in 3 categories. First-rate theory predicts. Okay, this is what we would like to achieve in nuclear modeling. The second-rate theory forbids. So it cannot perhaps predict, but provides constraints, okay, which eliminate. So this is good. A third-rate theory explains after the fact. And this is what is pretty common. We have models which try to explain or fit the data. Okay, so the goal, of course, is to develop first-rate theory for atomic nucleus, which will be predictive, which will allow robust extrapolations, which will allow validation of data, and most importantly, will provide guidance, short and long-term guidance. Okay. So it's difficult to give a talk on nuclear theory without showing the degrees of freedom, because theory depends on the resolution. Okay, so depending on what you want to see, what you want to understand, you take the relevant degrees of freedom. If you take the wrong degrees of freedom at your resolution, you will be very sorry. Okay? So we start from the most fundamental degrees of freedom, which are quarks and gluons. Those are the the degrees of freedom of quantum chromodynamics, and then as we move down in energy scale and down in the resolution of your probe, okay, we go to effective quarks, proton and neutrons and mesons, proton and neutrons interacting via effective forces, currents and densities and shapes. Okay, and here together with this, with integrating out the smallest degrees of freedom going in this direction, the typical theoretical approaches used at every level, lattice quantum chromodynamics, effective quark models, ab initio approaches for nuclear structure, configuration interaction methods such as nuclear shell model, density functional theory, and collective models. And the tool which lets us go from one area to another is the effective field theory. So this is our favorite theoretical screwdriver, which eliminates the degrees of freedom which are not necessarily important at our energy scale. Okay? So the first point I would like to make is that lattice is making tremendous progress. Lattice has put two nucleons on. So theorists put two nucleons on lattice, and they are able now to calculate not yet with at the proper pion masses, but at slightly higher, a little bit too heavy pions, the interaction or the effective potential between two hadrons or two nucleons like proton and neutron. So this is a six-body quark problem. Okay, so the first indications for the short range of the potential are coming from lattice. And if you keep track of the submissions to archive, you will see that there are first papers on few body systems, including strange particles. So I would expect in 4 years from now the first lattice calculations for alpha particles. Deuteron will be a little bit probably, for deuteron we have to wait longer, but alpha particle for many reasons is simpler to explain. Okay, so theory of rare isotopes is demanding. Okay, so this is a three-leg stool. The one leg is input. Input is important. If you have wrong input, even the best approach is not going to provide lots of insights. Second is dynamics, and the third is open channels, because nuclei are open systems, and especially exotic nuclei have low-lying thresholds, which of course are going to modify nuclear structure. So there's been a great recent progress in the terms of new ideas, in terms of wonderful input from experiment. So we learned that the data on exotic nuclei are indeed crucial, and there's been a great progress thanks to high performance computing. So this is the theoretical view of the nuclear landscape. The lightest nuclei in the landscape we can treat ab initio using the ab initio methods, which are based on 2 and 3 body interactions. Heavier nuclei can be treated well with configuration interaction approaches, which eliminate part of the space, treating this space effectively, and then density functional theory, which in principle can cover the whole landscape, but the nuclear energy density functional is yet to be found. Okay, and this is how those various approaches actually explain the nucleus. If you do have initial calculations, you can understand the nucleus in its full glory, with its mass and excited states and transitions and currents and whatnot. Configuration interaction introduces some simplifications, and DFT gives you the most global, most important properties. But each of those approaches has its, of course, range of applicability. Each of those is important, and great progress is happening in the intersections between those approaches. By understanding those links, we can go all the way from here to the nucleus. So let me show you, give you some illustrative physics examples now, and I will start from the frontier. The frontier right now is in calcium isotopes, okay, very neutron-rich calciums. This is where a lot of action is in terms of theory and experiment. This is where the best ab initio calculations using coupled cluster approach can basically illuminate density functional theory, okay? And you know this diagram very well. This is from a paper from ISOLDE in Nature. Those are two neutron separation energies in calcium isotopes. Very beautiful data here. Calcium 54 and 2+ measurement of 2+8 in the same nucleus at RICAN. Okay, so the point to be made is that you have those theoretical ab initio approaches like coupled cluster, many-body perturbation theory, which indeed provide good guidance, but naturally we see that if we go a little bit to the right, calcium 56 in this case, we have difference in predictions. So extrapolations are still a problem, and it's important to have the data on this one extra nucleus with 2 more neutrons. So calcium 56, as you can see, is certainly a very important system to be measured. The second example which I want to show are those microscopic shell model calculations in which the effective interaction is taken from ab initio theory. And there are 2 actually recent papers, one by on coupled cluster effective interaction using valence cluster expansion, Fisher Letters 2014, and in this same volume in medium similarity or normalization group effective interaction. So you take ab initio approach, starting from 2 and 3 body forces, and you calculate microscopically in the desired Hilbert space the effective force. Very nice comparison between experiment and theory. Okay, so this is something which is not yet published, but I believe it will create quite a splash. So this is the paper by Andreas Ekström et al., which has been just submitted to Fisher Letters. This is on the accurate nuclear interaction from chiral effective field theory for nuclear matter. So here the input is the chiral interaction, including 2 and 3 body terms. So these are calculations in the second order NQLO of chiral perturbation theory. So what you see in this paper is that this interaction was optimized in the 2 and 3 body sectors simultaneously. So it was unlike in the previous work where the first one worried about 2 body force and then 3 body force was added. Here 3 body force, and the data on heavy nuclei which were considered here informed actually the effective low energy coupling constants of the interactions. So the data, the interaction was adjusted to phase shifts, few body data like deuteron, triton, alpha particle, and also radii of oxygen and carbon. So with coupled cluster approach, one could actually do it, okay? And these are the results. So this is the agreement with phase shifts up to 35 MeV for the NN scattering. So the new interaction is called N2LO SAT because it provides saturation, and you can see here the residuals between experiment and theory provided by this interaction and by other models. And this is for binding energy, and this is for the radius. So for the first time, the radii of heavy nuclei are well reproduced, and these are the excited states. in the P and SD systems. This is the reproduction of oxygen-16 charge density by this interaction. So this is just a prediction. It was not fitted, and this is the saturation density. And by the way, the radius of calcium-40 and charge form factor of calcium-40 is also on target. So you have one course which does light, medium mass nuclei up to calcium-48, and it also does nuclear matter. Okay? So this is a good progress. So good progress has happened also in the area of small and large amplitude collective motion. So we are now at the level of microscopic description of nuclear fission, in which the fission pathway is obtained directly from effective action, actually minimization. So we now are able to describe the interaction between coexisting states microscopically using the modern models of large amplitude collective motion, and we can also predict cross-section for heavy ion fusion also at sub-barrier energies. And if you would like to see more, go to those papers. Okay? As I mentioned, nucleus is an open system, so there is strong coupling between nuclear structure and nuclear reactions. Good progress in this area as well. Two examples. One, ab initio calculations of asymptotic normalization constants and width by Knowledge using actually quantum Monte Carlo method, ab initio technique. And these are dineutron correlations in helium-6 using continuum shell model or gamma shell model. Okay? Very, very exciting area of progress. Okay? There's been very nice progress experimentally and theoretically in this area of fundamental interactions. Here, nuclear theory is badly needed to provide the missing link between the measurements and some fundamental constants. Of course, in the area of beta decay, supernovae beta decay, we need nuclear theory to extract to extract VUD matrix element of CKM matrix, and theory actually provides very good guidance when it comes to isospin mixing corrections. And research paper from here on pear-shaped systems in the radium-224 region. Here, this is important because in pear-shaped nuclei, a large shift moment can, of course, give rise to the electric dipole moment, a very fundamental quantity, which is now tackled in a number of places. So theory is needed here as well. Okay, prospects. Very good. So I have just 10 minutes from prospects, right? 7. Let it be 7. Okay. So our paradigm is scientific method. Okay. So theory makes predictions, creates a model, then this prediction is tested by experiment, by observation. Observation provides additional constraints and input to theory, and this cycle goes on. So it is important for us to speed up this cycle, actually to optimize this cycle, okay? Because we want to get progress faster. So some thoughts related to this cycle between experiment and theory. So beam time and cycles are difficult to get and expensive. Okay? So experiment keeps theory honest, and theory could help by being more involved in assessing the impact of plant runs and projects. Okay? There are many ways of doing this, and new technologies in developing theoretical uncertainties are essential for providing predictive capabilities to nuclear models, especially if one wants to do extrapolations to the areas which are not accessible to experiments, such as supernova or reactor cores or neutron stars or super heavy elements, which are which are well outside the range allowed by current beam and targets. So there's a paradigm shift needed to enhance the coupling between theory and experiment. So I would like to say a few words about the quality control, and this quote from British statistician E.P. Box is very actually relevant. Remember that all models are wrong. The practical question is, how wrong do they have to be to not be useful, okay? So sometimes it takes us a lot of effort, theoretically and experimentally, to eliminate wrong physics, okay? So I have a few examples to show here. The one is from the paper by Kortelainen et al. On neutron skin uncertainties of CERN density functional theory. What you see here is actually predictions of neutron skins, that is the difference between neutron and proton RMS radius for calcium, zirconium, erbium, and element 120 with two different models. What you see here is not only the prediction, the mean value, but also error bars. So in this theory it was possible, because covariance matrix was known from those interactions, to estimate theoretical uncertainties. Okay? So you see that while both theories are very close to each other, as we move towards the neutron drip line, our lack of knowledge about neutron, about isospin excess, manifests itself in those very large statistical error bars. Okay? And we can take those error bars and now we can make the balance. We can look what are the contributions to those error bars in those two models, and we see that the largest contribution to this uncertainty is the actually symmetry, is the density dependence of the symmetry energy. This parameter L, which also impacts quite significantly the mass to radius relation for the neutron star. Okay, so by measuring and by getting more information about this parameter L, one can reduce theoretical error bar on this quantity, and this will also help equation of state. Okay, the fact, of course, that models all agree far away in the region which is not tested by the data does not mean too much, because it might indicate that they are very precise, but they are not accurate. But this is a topic for another talk. Okay, so particularly painful here is this current quest for the nuclear matrix element, for the neutrino-less double beta decay. Various predictions for this quantity give rather large, show very large spread. So none of those calculations actually estimates the error bars. Maybe if error bars are added, we will see things like this. But we have to realize the difference between this number and this number means to go from 1 ton double beta neutrino experiment to 10 ton experiment, which is impossible. So the frustration because of the current status of matter has been nicely expressed by this neutrino-less double beta decay ENSAC report that theory must be improved here. Okay. So if you would like to see more about how theories need to actually move on with estimating error bars and providing uncertainties, I invite you to this website of the recent JPG focus issue on enhancing the feedback between experiment and theory, and you will see more stuff there. Okay, the last point I would like to make is about high-performance computing. Okay, so there are 3 legs of our field. One is analytic theory, experiment, of course experiment is first, then analytic theory, and then supercomputing, which is the third pillar of our field. Okay, so a few examples before I finish of what high-performance computing can do nowadays. Quantum Monte Carlo calculations for the carbon-12 the charge form factor and for the charge form factor of the point state. A comparison between ab initio Monte Carlo and measurements. Those are the calculations for the whole state structure using lattice EFT theory. Very nice recent work. This plot was already advertised by Gerd. So from this last density functional theory study, which tried to estimate uncertainties of the neutron drip line position. So this was also allowed by high performance computing, which made it possible to do lots of mass table calculations with various inputs. Okay, and we can now perhaps answer the question how many protons and neutrons can be bound in a nucleus. And this particular result as of 2012 says around 7,000 up to charge 120. So this is what was discussed today. A good progress in the reaction theory, where we can now do calculations like the recent work we could see on the archive, deuteron on alpha particle. 6-body problem, this was work by Triumph and Livermore, including 2 and 3-body force. Okay, so I have 2 summary slides. The first, so these are the challenges for low energy nuclear theory, and I believe that those are realistic challenges. I would not put on the slide things which are in the area of dreams. So we'll be able in few years to describe the lightest nuclei in terms of lattice QCD. This will be extremely important because this will provide the basic link between the effective forces which we use today and quantum chromodynamics. This will root actually our science in the fundamental theory of strong interactions. We'll develop first principles framework for light medium mass nuclei and nuclear matter from 0.1 of subsaturation to twice the saturation density. We'll develop predictive and quantified nuclear energy density functional theory rooted in first principles. We will unify the fields of nuclear attraction reactions. We'll achieve a comprehensive description of the most important reactions which are used to get information about nuclear structure. Will provide understanding of many body symmetries, and will develop predictive model of fusion and fission. Of course, as I discussed in my talk, it's very important to carry out quantified calculations with theoretical error bars. Okay, so this is a generic summary. Nuclear many-body problem is complex, challenging, and fascinating. So, we are celebrating the 50th birthday of ISOLDE. So, on behalf of many theorists, I would like to express thanks to ISOLDE for keeping us honest and providing fascinating data, which will constrain our models, and perhaps then we will make very nice predictions for you guys. So you will have interesting data for your proposals. And thank you very much for listening.